Hello everyone, my name is Anjiang Wei. Today I'm going to present our work on domain-specific fixes for Flaky tests with wrong assumptions on underdetermined specifications. This is joint work done by me and my collaborators, Peidun Yanjie, Victoria Darko, and August. I'm from Peking University, China. Let's begin with the background knowledge. Underdetermined specifications admit multiple implementations. These different implementations can return different output for the same input, even if each implementation itself is deterministic. For example, consider the method getDeclaredFields from the Java standard library. The Java doc specification for this method states that it returns an array of field objects representing all the declared fields for this class. And also, the elements in the return array are not sorted and are not in any particular order. In practice, the Java standard library has changed the implementation over time. For example, several widely used methods such as hashcode, HashMap, and HashSet iterators and get methods on several occasions broke substantial amounts of code. We call tests that fail due to making wrong assumptions on underdetermined specifications as implementation-dependent tests. Prior work has proposed NonDex, a technique to automatically find these ID tests. Recently, NonDex has been used in a large-scale study of Flaky tests, which can fail seemingly non-deterministically. They reported that approximately 30% of the Flaky tests in their dataset are due to such wrong assumptions. However, only partial support for manual debugging was provided by NonDex, and no automated fixing technique has been developed before. For this paper, our contributions are as follows. Firstly, we provide a novel dataset of 275 ID tests. This dataset is the largest for ID tests, showing the prevalence of this problem among open source projects. Secondly, we extend the existing NonDex tool to provide more info for debugging ID tests. Moreover, we derive novel strategies that can help to automatically repair the code exercised by ID tests. Lastly, we apply the DexFix technique on 275 tests, and we find that DexFix can propose fixes for 119 tests. Inspired by the fixes proposed by DexFix, we have opened GitHub pull requests for 102 tests, and 74 have been merged with only 5 rejected and the remaining still pending. Let me first talk about several real examples of how we fix ID tests. Apache Hadoop is a widely used open source project. NonDex detected several ID tests in Hadoop. Here we show one. It passes when run normally, but fails with NonDex, reporting an error message that appears challenging to debug. Fortunately, NonDex can provide useful debugging info for this case. The root cause here is that getDeclaredFields, which is invoked in reflection utils class. DexFix has a general automatic strategy called sort fields that sorts arrays of fields returned by getDeclaredFields at the call site from NonDex output, which makes the order of the elements in the array deterministic. We submitted this fix as a GitHub pull request, and the developer promptly accepted our fix. Let's proceed with another ID test. We can see the error message produced by NonDex that the order of elements failed the assertion. However, this time, knowing the call site is not enough. We only know that the failure is caused by the iteration over HashMap, but we don't know where the HashMap is allocated. To fix such a test, Xfix has a general automated strategy called hash to linked hash to replace allocations of HashMap or HashSet with linked HashMap or linked HashSet. The linked hash classes have a precisely defined iteration order. However, unlike in the first example where the test passed after the first change, the test again failed with NonDex after the change. The fix proposed by DexFix is actually composed of multiple changes in both main and test code. After we submitted this fix, the developer accepted it. Let's see this example from Alibaba Fast JSON project. As in the previous example, the root cause was with a HashMap iteration, and DexFix proposed the following change. However, after this change, the test still fails, and even without NonDex. The reason for this is because changing HashMap to linked HashMap makes the iteration order different from before. At this point, we run reassert to repair the failing assertion. reassert replaces the expected string with the actual string that the test produces. These two changes now make the test path both with and without NonDex. Our final example is in the case in JSON test from project Nuts, where DexFix proposes a fix just for comparing JSON strings. The root cause is getDeclaredFields in a third-party library. Luckily, the failed assertion just compares the JSON string to an expected value. DexFix has a general automated repair strategy that change such comparisons to use another assertion method, JSON assert equals, from a specific third-party library. The developers merged and appreciated our fix. Let's then proceed with our DexFix technique. The input to our tool conceptually consists of the project source code and one ID test to be repaired. The output of our technique is a fix consisting of one or more code changes that makes the test pass when run with NonDex. Intuitively, our strategies aim to make test assertion order agnostic or make output deterministic. Here we describe our repair algorithm on a high level. We believe that non-determinism used in the main code is not necessarily incorrect, so we think it's preferable to reduce flakiness in tests by making the test code agnostic to the non-determinism. So DexFix first tries to change assertions with no new dependencies introduced to make it order agnostic. If it does not apply, then DexFix tries to use hash to linked hash or sort field strategies we discussed before, depending on the root cause, and apply reassert if needed. If all previous strategies fail, then DexFix tries another assertion change as its last option because it can add new third-party dependencies to the project, and developers tend to be cautious about adding new dependencies. If you're interested in the pseudocode of DexFix repair process, please read our paper for details. Next, we discuss about the research questions proposed in our evaluation part. The first research question we address is the breakdown of the root causes and debug locations for ID tests. Results show that the majority fail due to the iteration of HashMap or HashSet. The second most common root cause is getDeclaredFields. In terms of debug locations, the majority are in the source code rather than in a third-party library. Our next research question is about the number of tests fixed by DexFix. The answer is that 119 tests are fixed. We find that hash to linked hash strategy contributes the most to fixing. Assertion change follows it, which supersedes source fields. We also show where the repair locations are. Only in the test code, only in the main code, or in both. We see a variety, demonstrating the importance of considering both main code and test code. Our final research question is about pull requests. Overall, developers have accepted PRs that we submitted for a majority of the fixed tests. This high ratio of accepted PRs shows the effectiveness of the fixes that DexFix proposes. For those rejected or unsubmitted ones, please see our paper for details. In conclusion, we present the DexFix approach for automatically fixing implementation-dependent tests that fail due to wrong assumptions on underdetermined specifications. DexFix extends the work on repair with novel, domain-specific automated repair strategies that can propose fixes for either the main code or the test code or both as necessary. Out of all detected ID tests, DexFix proposed fixes for almost 43% of them, and we have opened pull requests for 102 tests with the majority merged. Our dataset and GitHub pull request links are publicly available. We hope that DexFix will inspire more research into domain-specific repair, not just for ID tests, but also for other types of flaky tests and bugs in the main code. If you have any other questions, please feel free to contact me. Thank you.
All right, thank you for that presentation. Welcome everyone. If you're just joining us, this is the session on API development. I'm Carolyn Seaman from UMBC in Baltimore in the US, and I'm your session chair. And I have with me Anjang, who is ready to take your questions. So put them in the chat. And while you're doing that, I will start us off with a couple questions of my own. So Anjang, I was wondering, in your future work, in your presentation, you talked about how you want to look at domain-specific repairs for other types of flakiness. And so I was wondering what other domains you're thinking of looking at and what other types of flakiness you might address in your future work.
Oh, that's a very good question. For flaky tests, there are many other types of flakiness in testing, including a major part is called order-dependent flaky test, which means the outcome of the test depends on the order of the test you execute, right? So other types of flakiness include floating point errors, networks, IOs, and time. Also, some randomness in the algorithms will also sometimes break the test. So these can all contribute to the so-called flaky tests. And so for future work, I think especially for network and IOs, they are really hard because it's an external. It's related with the external state of the system. But for floating point errors and also randomness in algorithms, especially some hot topics like AI, they also have some. Their training algorithms are also have much randomness in their algorithms, so they are really interesting topics in the future that we would like to address in the future.
Okay, great, thank you. All right, folks, we still don't have any questions in the chat from the audience, so I think people need to wake up a little bit. You're all from North America, right? And it's morning. Yes. But in the meantime, I have another question to get us going. My other question is, I wonder, some of the fixes that you submitted were rejected. And I wonder if you could give us a sense of some of the reasons that they gave for rejecting some of your fixes.
Oh, yes. That's discussed in the paper, but we didn't say anything in the presentation. But I'm glad to give an overview of why these fixes are rejected. So one rejected PR involves some JSON assertion, and because it adds a new dependency to the project, and so the developer thinks that it's a bit it's not satisfactory to add something big for a flaky test for a small problem. But they acknowledged our contribution. They said in a message, they sent in the chat that, oh, I've changed the test accordingly, and thanks for your hint. And their fixing way is using some project-specific annotations for specifying the order and using some sorted maps. And it's their own way of fixing. So we regarded their fix as a rejection for our own pull request. So, and also there was in another project, the developer rejected our pull request for similar reasons, because they don't want to add a third-party dependency, especially a new dependency for this flaky test. And they said, oh, we never had such problems with this test, and so we would not want to change it. So
it's
we
not broken, don't fix it, right?
Yes. And also there are other kinds of rejections, but it's fully discussed in the paper. I cannot remember all of them. So if you are interested, please go and read our paper for details.
Absolutely, thank you. All right, we have a question from Na, who says, thank you for the talk. First of all, in the presentation, you introduced some patterns for flakiness and the corresponding fixes. I'm curious how many patterns are included in this research. How did you identify these patterns in the first place? How are these patterns represented in your tool? Are they hard-coded or somehow specified with a domain-specific language? So there are several different questions in there. I'll let you decide what order you want to take them in.
Oh, that's a very good question. And so for this research, we focus on the root causes that we identify for the most common causes. That is the getDeclaredFields and the HashMap or HashSet iterations stuff, right? As we discussed in the presentation. But there are other there are other sources of flakiness in terms of the underdetermined specifications, including get methods and get fields, get type annotations, some rarely used APIs. But we don't fix those APIs because they are so rarely used and don't merit developing a new strategy. So we only focus on the major and the most common root causes, and that's what our patterns are focusing on, right? And how are these patterns represented in our tool? So our tool basically the input to our tool is code, right? Is the code. So first it parses into an abstract syntax tree, and then it do some code transformations to create the fix. And so basically, and also for JSON strings, we have some special domain-specific recognition methods to recognize that, oh, this is JSON string comparison, JSON object comparison, that kind of stuff. And are they hard-coded or somehow specified with domain-specific language? So it's not specified with a domain-specific language. It's more likely to be hard-coded with, but it's a general strategy. It's not like a string. It's not as simple as string substitution, but it's not it's also not that not as difficult as a new domain-specific language.
All right, thank you. All right, any more questions from the audience? Please put them in the chat. We'll give you a couple more seconds. And if not, we can end the Q&A a little bit early, but just a reminder, there will be a discussion room. The link to that will pop up in about 2 minutes. So if you're interested in going into the discussion room, stick around and wait for that link to come up. And Anjiang, you can stay here, you can leave room and then watch the stream so that you see the link to the discussion room. Or you can just stay here and turn your camera and mic off and wait for that link to come up at the end of the Q&A session, okay?
Okay.
Thank you. Na says thanks. Yes, thank you very much for your answers. And I think we'll end the Q&A now. Thank you, everybody.